Hello, my name is Michael Vriedeveld, and this is my submission for my Physics Lab 2 Motion of a Falling Object. Today I will be doing an analysis of a system falling from rest. My system is a crumpled up newspaper from the Georgia Tech Technique. I took the mass of this system to be 0.12 kilograms or 12 grams. And since it is falling from rest, the initial velocity is 0 vector meters per second. The problem today was to analyze a system falling from rest and examine the forces acting upon said system as it falls. To do this, we're using Newton's second law, V final equals V initial plus F net over mass delta T. Initial velocity, as I said, is 0 due to the fact that it's starting from rest, and the net force is being calculated from the gravitational force being added to the drag force or air resistance force. Here I will show you my tracker recording depicting the paper ball which fell from a height of about 2 meters. As you can see, it fell in the negative y direction because of gravity, and you can see the graph right here to the upper right hand corner. You can see that it does indeed accelerate at the beginning, but reaches terminal velocity around 0.4 seconds. Here I will show you the computational model that I also did to be able to predict the falling motion of the crumpled up paper system. As you saw from the arrows in the dropping sphere, the yellow arrow pointing down is the constant force of gravity in the negative y direction, and the blue arrow, which points up and starts off small and grows bigger and bigger in magnitude, is the drag force, which as the velocity increases, the drag force also increases. Here I will show you my graph. In this graph, it is depicted the blue dots are my experimental position, where is the position versus time of the tracker video. The red line is the model position of the model that I used where there is no drag force. The yellow is the model position where I used drag force as the equation negative b times velocity squared. And the green is the same idea, or the same drag force, except it is negative b times velocity. As you can see, the model position extremely overpredicts the experimental position due to there not being any drag force. And the green and yellow model positions differing in negative b times v squared versus negative b times v. The drag force where it was used negative b times v fits the experimental position slightly better due to the numerical value of negative b. The numerical value of negative b was calculated to where the endpoints of the experimental position and the endpoint of the model position would meet right here. Through this experiment, it was seen that the model position with drag using FD equals negative b times v fit the experimental position better. However, in the center region did not fit very well. This could be due to differences in air resistance as well as the overall density and structure of the crumpled up paper ball, since it is not uniform. In this chart, we show the difference where if the object had been thrown instead of dropping from rest. The red depicts it as the crumpled paper ball system being thrown, and the blue is where it drops from rest. As you can see, the model position for the thrown paper ball does go a little farther. However, the terminal velocity, the slope of the terminal velocity, is the same as the model position.